Scalar triple product. Let's see what a triple product means. We have already seen the product between two vectors. So we have seen A dot B and A cross B. This is, we know this is called the dot product and this is called the cross product. B dot C is a scalar. The result is a scalar. B cross C is a vector. Right? So remember this. Now, what if there is another vector, third vector? So a product of three vectors is called a triple product. Okay, so what are the possibilities? A dot B cross C, A cross B cross C, A dot B dot C, and A cross B dot C. Now if you look at this is a scalar. This is also a scalar. So this becomes a product between a vector and a scalar. A vector and a scalar. So this actually is not relevant because here we are talking of a product of vectors. Okay, so the only things that make sense is this one and this one. This is called the scalar triple product and this is called the vector triple product. Okay, let's look at scalar triple product in more detail. Now, A dot B cross C is denoted by, can also be written as A, B, C. So it's also called as box product. Let's say vector A is A1, A2, A3. Vector B is B1, B2, B3. And vector C is C1, C2, C3. A dot B cross C, A1I plus A2J plus A3K dot, remember vector A can be written like this in terms of the components. Okay, and B cross C we have already seen can be written in determinant form. So J, K, B1, B2, B3, C1, C2, C3. So this would be equal to, if we multiply A1 I square is 1. So which means A1. Similarly, A2, J square will be 1. K square will be 1. So B1, B2, B3, C1, C2, C3. Okay, let's look at the second aspect. A dot B cross C is equal to B dot C cross A, which is equal to C dot A cross B. So here if you notice what is happening, it is cyclic in nature. Now let's start from any one point. Let's say we start from B dot C cross A. Now this would be B1, B2, B3, C1, C2, C3, A1, A2, A3. If we substitute R1 with R3, we would get what? We would get a minus of A1, A2, A3, C1, C2, C3, B1, B2, B3. So this is one of the properties of the determinants. If you exchange the rows, then the sign changes. Now that we have done this, exchanged A1 and A and B's, now we have to exchange the C and B's, right? So let's exchange R2 and R3. So what do we get? We get again minus of minus is plus. So this becomes A1, A2, A3, B1, B2, B3, and C1, C2, C3, which is nothing but A dot B cross C. So what this basically means is that the cyclic permutation of three vectors does not change the value. Okay, let's look at the third aspect. A, B, C is equal to minus A, C, B. Just remember, we have exchanged the rows, so it becomes negative. Similarly, minus of B, A, C. Similarly, C, A, C, B, A. An anti-cyclic permutation changes the sign of the product. There is no change in the magnitude. Okay. A dot B cross C is equal to A cross B dot C. That means you can exchange the dot and cross, are interchangeable. Okay. A cross B dot C is equal to C dot A cross B, which is equal to A dot B cross C from the previous property we have seen, previous aspect we had seen. So that means this is commutative. So here we have dot and cross we have interchanged, but one of our previous aspects that we had seen was that the cyclic permutation. Based on that, we can say that this is equal to A dot B cross. When 2 or 3 vectors are collinear, the scalar triple product is 0. If A and B, let's say, are collinear, then B would be equal to MA. So A, B, C would be equal to A1, A2, A3, B1, B2, B3, C1, C2, C3. Now, because of this, let's say B is a multiple of A. Okay, so which means B would be equal to MA. Yes. So what will happen here to the determinant? A1, A2, A3, MA1, MA2, MA3, C1, C2, C3. Now remember, when one row is a multiple of another row, the determinant becomes 0. So this is equal to 0, since R2 is equal to R1. So which means if 2 of 3 vectors are collinear, then the triple product is 0. So let's say we have A, B, C as coterminal A, B and C. So this is let's say B, this is C, and this is A. Now B cross C. So let me write it down. This is O, this is A, this is B, and this is C. So OA is equal to A, OB equal to B, OC equal to C. Let's keep adding parallel vectors, parallel and equal vectors to each of these vectors. Build the parallelepiped. This figure is called parallelepiped, whose co-terminal edges are the vectors A, B, and C. Now B cross C would be what? B cross C would be the perpendicular to both B and C. Right? Okay, so this would be B cross C. And let's drop a perpendicular from here, from A to B cross C. And let's call it as M, that point. Now remember, B cross C, this is B, this is C, the product of that is B cross C, which is perpendicular to both. But the magnitude of B and C, is the area of this parallelogram, right? So is equal to area of the base of the parallelepiped, which is nothing but the parallelogram. So now we do a dot product with BC, B cross C. What do we get? We get the magnitude of C dot projection of A onto B cross C. Projection of A onto B cross C. So this is nothing but OM. So this becomes area of the base times OM, which is the height. And this is what? This is the volume of the parallelepiped with A, B, and C as co-terminal vectors. So which means scalar triple product gives us the volume of the parallelepiped with ABC as co-terminal edges. Okay, that's interesting. If ABC are on the same plane, it means what? The height, that is B cross C, is equal to 0, right? Which means volume is equal to volume of the parallelepiped is equal to 0. So therefore, if the scalar triple product is equal to 0, it implies that A, B, and C are coplanar. That means they lie on the same plane. And finally, if you have 4 points A, B, C, D, they will be coplanar if the triple product, more specifically scalar triple product of AB, AC, and AD, that means co-terminal vectors, is 0, or AB, BC, and CD is 0. Remember, we can move the vectors provided the magnitude and the direction remains the same. Okay, so that is scalar triple product. Bye for now. See you again.